So, good evening, everyone. Let us continue our discussion for the 6th week lecture. So, in this week's class, we will basically be understanding thoroughly the ISO 14040 code. That is basically the code on life cycle analysis. So, we'll basically try to understand further and like properly understand the terminologies associated with life cycle inventory, life cycle impact assessment, and interpretation, along with the goal and scope. And uh, Carrying forward, basically we will thereafter try to understand the various types of chemicals which are released into the environment, and also the need for the creation of sustainable or green materials. Okay, so let us start our discussion. So the lecture 26 is on ISO 14040. ISO stands for International Standardization Organization. So let us, based on the discussions we have had in the past classes, let us now properly, like formally, try to coin the various terminologies which we studied. Okay, so let us have the standard definitions for all the terms. So these are as follows. So life cycle inventory (LCI) it is basically phase of LCA involving the compilation and quantification of inputs and outputs for a product throughout its life cycle. Life cycle impact assessment (LCIA) it is phase of LCI aimed at understanding and evaluating the magnitude and significance of the potential environmental impacts for a product system throughout the life cycle of the product. Interpretation is basically phase of LCA in which the findings of either the LCI or LCIA or both are evaluated in relation to the defined goal and scope in order to reach conclusions and recommendations. So the product system basically it is the collection of unit processes with elementary and product flows performing one or more defined functions and which models the life cycle of a product. And the unit processes are basically the smallest elements which are considered in the life cycle inventory analysis for which input and output data are quantified. So in that there is elementary flow, which is basically material or energy which is firstly entering the system that has been drawn from the environment without previous human transformation, or leaving the system that is leaving the system that is released into the environment without subsequent human transformation. And that is the elementary flow. And so one more is the intermediary flow. So that is basically the flow which connects between two unit processes, that is product material or energy flow occurring between unit processes of the product system. And one more is the reference flow. It is basically measure of the outputs from processes in a given product system required to fulfill the function expressed by the functional unit. So these are some of the standard terminologies, definitions of the life cycle terms as per ISO 14040. So these are some of the also some of the terms like impact category, LCA results category, indicator, characterization model. So we have studied this in the last class: characterization factor, category, indicator, result, category, endpoints. So there are some examples based on that also. So as you can see here. So again, so what is the definition of LCI result? So it is basically outcome of a life cycle inventory analysis that catalogs the flows crossing the system boundary, and that is basically equal to the elementary flow, because that is a flow which is coming outside the system and which is coming into and going out from the system. Okay, so that is the system boundary. So basically that is equal to the elementary flow, and it provides the starting point for life cycle impact assessment. uh, Example, kg CO2 per functional unit. Similarly, the impact category, it is basically the class representing environmental issues of concern to which life cycle inventory analysis results may be assigned. Each category has its own environmental mechanism. Example, global warming. So there are various impact categories, say global warming, non-renewable energy. Okay, so yeah, even the CO2 release can be an impact category, or say for example eutrophication. We have studied all of this in the last classes, if you remember. So apart from that, there is environmental mechanism. So that is system of physical, chemical, and biological processes for a given impact category, linking the life cycle inventory analysis results to category indicators and to category endpoints. And there is impact category indicator, which is basically quantifiable representation of an impact category. Its goal is to reflect all the extractions or emissions assigned to an impact category. Example, infrared radiative forcing, watt per meter square. So that was, if I remember, it was the first degree of effect. Okay, so due to global warming, the first degree of effect was the infrared radiative forcing. It is in watt per meter square. So apart from that, there is characterization model. So as you saw in the table, so it reflects the environmental mechanism by describing the relationship between the LCI result and the category indicator, and in some cases the category endpoints. It is used to calculate the characterization factors. So what is characterization factor? It is factor derived from a characterization model which is applied to convert and assign life cycle inventory analysis result to the common unit of the category indicator. The common unit allows calculation of the category indicator result. For example, kg CO2 equivalent by kg GHG, that is greenhouse gas emitted. So what is category endpoint? It is basically an attribute or aspect of natural environment, human health or resources, identifying an environmental issue, giving cause for concern. Example, human health, ecosystems such as coral reefs, forests, crops, etc. So what is sensitivity analysis? So it is systematic procedures for estimating the effects of the choices made regarding methods and data on the outcome of a study. What is uncertainty analysis? It is basically a systematic procedure to quantify the uncertainty introduced in the results of a life cycle inventory analysis due to the cumulative effects of model imprecision, input uncertainty, and data variability. Critical review, it is basically a process intended to ensure consistency between a life cycle assessment and the principles and requirements of the international standards on life cycle assessment. So these are some of the standard terminologies as per ISO 14040. So now let us go to the next lecture, which is basically key points of a good LCA and example LCA. Let us see. So good points for a good LCA is basically in goal and scope. There is the screening approach where there are two steps. One is first screening level LCA to get order of magnitude results, and second detailed LCA to refine results and most important contributors. And the second part is goal of the study, very clearly defined the what for, and for who. Okay, these three terms should be clearly defined for the goal. The third part is function and functional unit. So function of the system is the starting point in defining the system boundaries, comparison on the basis of the same function, secondary function, and it may be a secondary function. So that is the function of the system, and for representing that we have functional unit fu. So this quantification of the function of the system, it is never a ratio, and in inventory is related to fu basically. And reference flows, amount of product per provide fu, different for the compared systems. And key parameters, it links between fu and reference flows, that is optimization. Okay? So these are some of the uh, important parameters in goal and scope. So fourth is the system boundaries. So all processes needed to provide the function. So first rule is compared systems must provide the same function. Second rule, included processes are those which contribute more than a fixed percentage of mass, energy or environmental relevance cutoff criteria. The third rule is identical stages or processes between compared systems can be excluded only if this does not affect functional equivalence. So these points have to be kept in mind. So now let us go to inventory. So for inventory, the important point is data quality, because it is basically the stock of data which we have uh, which we have uh, which are available with us for performing the life cycle. So validity of the study depends on the quality of the data used. So it can be geographical, temporal, that is time and technological coverage, and also one of the important characteristics is its uncertainty. The sources can be primary, which is the sources has to be one is the primary, that is a specific reason for which we need the data, and secondary type of data is the general type of data which is not our first priority, but we can use that for performing some other type of analysis, finding some other, interpreting some other facts about the process. The second part is the multifunctional processes. There are several approaches to treat multifunctional processes. The results are often strongly influenced by the approach choices. Test robustness of conclusions by applying other approaches. So these are the factors, and so these are the important points to remember in inventory. Now let us go to impact assessment. So the impact evaluation is always done according to the goal and scope. Only use renowned and peer-reviewed methods. Must consider the fate and effect of emissions. So fate is basically when something is released into the environment. Okay, so that is fate. Okay, some chemical or some anything as output is released to the environment. Okay, so test robustness of conclusions by using other method or methods. So these are some of the points. And the last is the interpretation. So for that, analyze contributions at different levels at each phase of the LCA inventory impact evaluation, at each life cycle stage, concentrating on main contributors and those with the high potential for reduction at a substance level. So do sensitivity analysis to test robustness of conclusions, scenarios, uncertainty. So therefore, in a nutshell, let's summarize what is LCA. So LCA is a way of structuring, organizing the relevant parts of the life cycle. It is a tool to track performance and perhaps to improve product design. LCA is not a cure-all for our environmental problems. LCA is not an exact science with provable axioms or theories. So what is LCA? It is basically a tool that assesses a product or processes impacts in terms of environmental, social and economic. And there are multiple approaches to LCA. Okay, so it can be cradle to grave, which is the best one. And apart from that, there it can be cradle to gate, cradle to cradle, gate to gate, and well to wheel. So well to wheel is basically it is for the fuels. Okay, fuels, that is including all phases of its life cycle from the extraction of the fuel of for based on the raw materials to their use. Okay, and this is the framework basically, which is having three parts: goal, scope, inventory analysis, impact assessment, and all of them are connected to interpretation. So based on the interpretation, we have to again come back. So all are interrelated basically. The main point is the interpretation, and for that we have to consult all the three. So total is 4 points and main are the 3 points, and we have to interrelate all of them. Okay, so LCA is basically a technique to assess the environmental aspects and potential impacts associated with a product, process, or service by compiling an inventory of relevant energy and material inputs and environmental releases, evaluating the potential environmental impacts associated with identified inputs and releases, interpreting the results to help decision makers make a more informed decision. So these are some of the characteristics of LCA. So let us take an example. So let us take an example of Dongara. Okay, so this is basically a waste to energy plant that processes residential MSW, that is municipal solid waste, as a feedstock to manufacture a pelletized fuel product. Okay, feedstock is basically raw material required for some industrial process, and pelletized is basically any form or shape in granule type. Okay, so any granule type form or shape is pelletized. So how Dongara plant converts waste to energy in terms of like developing pelletized fuel product from feedstock. Okay, which is basically a waste material. Okay, so we will study that. So this plant is basically located in Vaughan. So Vaughan is a place in is a small municipality town in Canada. So processes MSW from the Great Toronto area and the regions of York, Durham and Peel. Processes approximately 75,000 tons of MSW per year. Okay, so this is the picture of that plant. So the fuel basically which is developed is this pelletized fuel, and that is basically the name is NRPX Plus. Okay, so this is the name of the product. So NRPX Plus is the fuel product produced at Dongara. It is used as a substitute for fossil fuels, contains an energy output of 10,000 BTU, that is British thermal units per pound, and utilizes approximately 60% of the incoming waste in producing the pellet. So the goal, definition and scope in this case will be: the goal of this study is to assess the environmental impacts of NRPX Plus in comparison to medium grade coal. Compared to medium grade coal, since NRPX Plus has similar energy content, the analysis was performed from cradle to gate. Okay, so why not cradle to grave? Because combustion properties and information of NRPX Plus were unavailable to perform a cradle to grave analysis. So it is the best analysis, but if all the information is not available basically related to combustion and properties and information of NRPX Plus related to its disposal, so the disposal or the last stage basically, so if it is not available, so That's why the analysis has had to be performed from cradle to gate. Okay. The chosen function for the analysis is providing energy through combustion. Therefore, a functional unit of 992 giga BTU, that is British thermal units, was selected to compare both NRPX plus and medium grade coal based on the total input of 75,000 tons of municipal solid waste. Okay, so here are some of the assumptions and limitations. Okay, that has been taken in the study. General assumptions are facility assumed to be a black box. So basically, we don't know what is happening in between. Okay, we only know about the input and output. Okay, only inputs and outputs are considered. Assumed 75,000 tons of MSW annually processed at Dongara. Assumed waste was strictly coming from the region of York. It is a place in a small town in Canada. Average distances traveled by a collection truck from curbside, that is a truck which is parked near the edge of the sidewalk beside the road. So the distance travel by the collection truck from curbside to plant was 41.4 kilometer. Collection truck capacity of 18 tons, okay, or 18,000 kgs, kilograms. Coal production scenario, basically, we just assumed it to be cradle to gate analysis. Only the production of medium grade hard coal briquettes. Briquettes is basically a small brick made of compressed coal, okay. And the incineration scenario, so total MSW sent to incineration, that is burning, and distance traveled in transportation is identical to that in NRPX plus LCA. Okay, so these are the incineration scenarios. Okay, so now if we break down the MSW, okay, municipal solid waste. So if you see here, so the NRPX plus, okay, so that is basically only releasing the four types of municipal solid waste out of the nine. Okay, out of the, yeah, out of the nine. So four only they're releasing. One is organics, which is 20.25%, which is equal to the assume. One is plastic film, which is 6.47%. So we assume 25.07, which we have assumed it to be the conventional. Okay, but we had to reject 18.6 because this was not coming, so only coming was 6.47%. Similarly, paper and cardboard, there was no rejection, so it was the same as conventional, 19.52, and wood also same as conventional, 13.77. So leaving all these three and all these four, so rest there is no municipal solid waste coming from NRPX plus, because assumed is equal to rejected, that is nothing is there, okay, from NRPX plus. So that is its advantage, okay, benefit. So assumptions breakdown of MSW, if you see, so there is organic waste comprising 30% food waste, which is basically fruits, vegetables, meat and fish, rice, bread. Textiles 6% is coming in form of jute, cotton and canaf, and rubber 3% in the form of synthetic rubber, and yard waste, which is grass, it is accounting about 61%, that is the majority. Okay, metals, there is 100% aluminum, and paper and cardboard, paper is 50% in terms of waste paper, and cardboard it is 50% in terms of corrugated board, that is a board which is not straight, okay, it is wavy pattern. Okay, so the rejected waste, if you see, so the plastic film. Okay, so plastic film, the percent rejection is 74.19%. Okay, and the disposal method is landfill. The hard plastic is 100% landfill, glass 100% in landfill, metal 100% is recycled, PVC polyvinyl chloride 100% landfill, and non-combustibles 100% landfill. So results is like we have to see the LCA of we saw the LCA of NRPX plus at Dongara, LCA scenario for coal and LCA scenario for incineration. Okay, so the environmental impact assessment summary can be such that NRPX plus has less impact on environment than coal for most of the impact categories. NRPX plus has a better impact on environment than incineration. Most sensitive impact categories are climate change, marine ecotoxicity, marine eutrophication, ionizing radiation, and terrestrial ecotoxicity. And major contributors to environmental impacts include electricity usage, disposal of plastics, organic waste, and metals. So, based on this, what are the conclusion and recommendations? According to the results, NRPX Plus is an environmentally positive substitute to medium grade coal. Possible alternate treatment of MSW instead of incineration. Possible room for improvement in reduction of environmental impact. According to the results, reduction of energy usage is recommended. Energy audit may be beneficial in locating inefficiencies in production process. Leachate generated due to landfilling of rejected plastics. Dongara may want to consider collection and recycling of plastics. Implementation of renewable energy sources. Example, solar panels to supplement required energy is recommended. So these are some of the conclusions and recommendations. So this is all about how to do the LCA and the various terminologies as per the ISO 14040, which need to be understood properly before carrying the LCA. Now let us go to the next topic, which is chemical release in environment. So environmental releases, okay. So a material at the end of its useful life cycle or as a consequence of its production or use is released into the environment. So will its release pose significant environmental or human health risks? Will the chemical degrade in the environment or will it persist? So this is the table 4.4, which is showing chemical properties needed to perform environmental risk screenings. Okay, so these are some of the environmental processes: dispersion and fate, persistence in the environment, uptake by organisms, human uptake, toxicity, and other health effects. So basically, fate is, as I told you, what happens to the contaminant, chemical, or biological substance after it's released into the environment. Okay? So relevant properties for dispersion and fate. Dispersion, we all know, it is basically flow of a the flow of a chemical from the higher concentration to a lower concentration, basically. So this is the movement. Okay, so relevant properties: one is volatility, density, melting point, water solubility, effectiveness of wastewater treatment. Persistence in the environment: so persistence is basically length of time a contaminant remains in the environment before being transformed by chemical and or biological processes. So for that we have to find these properties: atmospheric oxidation rate, aqueous hydrolysis rate, photolysis rate, rate of microbial degradation and absorption. Uptake by organisms. So for that we have to find the volatility, lipophilicity. So that is basically the tendency of a chemical to dissolve in fat, lipid rather than water aqueous environments. Okay. So apart from that, there is molecular size, degradation rate in organism, etc. Human uptake, basically it is a transport across dermal layers, transport rates across lung membrane, degradation rates within the human body, toxicity and other health effects. So those response relationships are there. So let us study in detail what is persistence of chemicals. So it was the length of time a contaminant remains in environment before being transformed chemically or biologically. So once the basic chemical and physical and chemical properties are defined, a series of properties that influence the persistence of chemicals in the environment are estimated. These include estimates of the rates at which chemicals will react in the atmosphere, the rates of reaction in aqueous environments, and the rates at which the compounds will be metabolized by organisms. If environmental concentrations can be estimated based on release rates and environmental fate and persistence properties, human exposures to the chemicals can be estimated. These chemical and physical properties can be used to evaluate a variety of metrics related to environmental impacts. Some of the most commonly evaluated environmental metrics are persistence, bioaccumulation, that is the gradual accumulation of substances such as pesticides or other chemicals in an organism, and toxicity, what is its harmfulness. Okay, so this is the example of a gasoline spill. Okay, so this spill has occurred. So this was the liquid gasoline. Okay, and the spill has occurred. So that will result in this will basically result in residues. Okay, so this residue will result in vapor. Uh, this one vapor diffusion, and in the vapor diffusion will basically happen in the soil. Okay, and then vapor will be released to atmosphere, and in presence of wind it will flow. Okay, and there is this building also, so it can also the flow can also go from the soil to the building. And apart from that, below the liquid gasoline there is water table, basically groundwater table. So there we will observe a dissolved plume. Okay, so plume is basically long cloud of smoke or vapor resembling a feather, bird's feather, as it spreads from its point of origin. So if you see here, it is like almost a feather. Okay, the structure is almost that of a bird's feather. Okay, so that is why it is called dissolved plume. So this is the example of fate and transport problems. So it is the leaking storage time in the surface. So the first location is plutonium. Okay, then there is rare earths. Okay, so it will pass through all this cesium, strontium, ruthenium, nitrate, and there is this groundwater level. So monitoring wells are there also. So contaminant leaking from a discharge site of radioactive waste. Okay, so if the contaminant is leaking from a site of radioactive waste, so it can be very harmful. So leaching is the basically, if you see here, so leaching waste is there, and it is also taking almost a form of plume. Okay, inside the groundwater table. Okay, this is flow. So leaching is the process of draining away material from a substance through the action of percolating liquid, especially rainwater. So rainwater is coming, and this is so say for example you had dumped waste in this place, you had landfill the waste here. So due to leaching, the material will get away from the substance. Okay, and it will flow. Okay, so that is also problematic issue. And apart from that, the if you see here, so this is a basically a figure which shows the reduced species created and oxygen being reduced, and for them the various EH values, that is redox potential in millivolts. So for water and oxygen, this in this place the EH value lies between 600 to 900, and that is aerobic respiration. And in ammonium and nitrate ion, so it is the range, it is close to 600 millivolt, and it is denitrification. Between MnO2 and Mn2 plus, it is less than 600, and manganese reduction between ferrous iron oxide hydroxide and ferrous ion, so it is basically close to zero, and it is iron reduction. In case of sulfate ion and bisulfide, it is more than minus, so it is about close to this one, minus 300, so it is sulfate reduction. And then CO2 and methane, it is methanogenesis, which is minus 300 almost. Okay, so the methanogenesis is the production of methane by bacteria or other living organisms. Okay, so variability is from slow reaction kinetics and changes in species concentrations. Okay, so, to further understand properly the about the release of chemicals into the environment, there are some properties and the terms along with the definitions and significance. Let us see that. So, one is melting point, TM. So, it is temperature at which solid and liquid coexist at equilibrium, and it is sometimes used as a correlating parameter in estimating other properties for compounds that are solids at ambient or near ambient conditions. One is boiling point, which is TB. So temperature at which the vapor pressure of a compound equals atmospheric pressure. The normal boiling points temperatures at which pressure equals 1 atmosphere will be used in this text. Okay, and it characterizes the partitioning between gas and liquid phases. It is frequently used as a correlating variable in estimating other properties. And vapor pressure, which is PVP, so it is the partial pressure exerted by a vapor when the vapor is in equilibrium with its liquid. It characterizes the partitioning between gas and liquid phases. So apart from that, there is the Henry's law constant H. So it is the equilibrium ratio of the concentration of a compound in the gas phase to the concentration of the compound in a dilute aqueous solution, so sometimes reported as atmosphere meter cube per mole. The dimensionless form will be used in this text, which is Ca equal to HCW, and it characterizes the equilibrium partitioning between gas and aqueous phases. One property is the octanol water partition coefficient, which is KOW. So it is the equilibrium ratio of the concentration of a compound in octanol to the concentration of the compound in water, that is CO equal to KOW into CW. It characterizes the partitioning between hydrophilic and hydrophobic phases in the environment and the human body. It is frequently used as a correlating variable in estimating other properties. Then there is water solubility S. So this is equilibrium solubility in mole per liter. It characterizes the partitioning between hydrophilic and hydrophobic phases in the environment. So apart from that, there is soil absorption coefficient KOC. That is basically equilibrium ratio of the mass of a compound absorbed per unit weight of organic carbon in soil in microgram per gram organic carbon to the concentration of the compound in the water phase in microgram per millimeter, that is CS equal to KOC into CW. So it characterizes the partitioning between solid and liquid phases in soil, which in turn determines mobility in soils, frequently estimated based on the octanol water partition coefficient and water solubility. And the last is the I think yeah. So last is the bioconcentration factor (BCF), which is ratio of a chemical's concentration in the tissue of an aquatic organism (CaO) to its concentration in water reported as liter per kg. So CaO is equal to BCF into Cw, and characterizes the magnification of concentrations through the food chain. Okay, so these are some of the standard definitions of the important properties. Okay, so using property estimates to evaluate environmental partitioning, persistence, and measures of exposure. The problems associated with estimating environmental exposures are complex. We need to consider a relatively simple example of calculating exposure through drinking contaminated surface water. Let us assume that a chemical is released to a river upstream of the intake to a public drinking water treatment plant. So to evaluate the exposure, we would need to determine firstly what fraction of the chemical was absorbed by river sediments. Secondly, what fraction of the chemical was volatilized to the atmosphere. Thirdly, what fraction of the chemical was taken up by living organisms. Fourthly, what fraction of the chemical was biodegraded or was lost through other reactions. And fifthly, what fraction of the chemical was removed by the treatment processes in the public water system. So the direct use of properties to categorize the environmental risks of chemicals. So the chemical and physical properties can be used to estimate environmental footprints. The another approach is to use the values of properties to directly categorize the environmental risks of chemicals and to classify the persistence and bioaccumulation of chemicals. So these are this table denotes the classification criteria for persistence and bioaccumulation. So if you see here, these are some of the properties related to water solubility, and these are the classifications provided. And similar is the case for soil sorption. So what is sorption? It is the process by which a substance, which is called the sorbate, it is basically sorbed, okay, which can be in the form of absorption or adsorption, okay, in another substance which is called sorbent, okay. So a substance sorbate which gets either adsorbed or absorbed in another substance called sorbent. This process is called sorption. Okay, so these are some of the classification based on which we can say it to be very very water soluble or very strong sorption, so normal, strong, okay, moderate, low, or insoluble or negligible. Okay, so these are some of the classifications. And also there are classifications for biodegradation, the rate of biodegradation, and bioaccumulation potential. Okay, so for each of these categories a score might be given. For example, persistence might be scored 1 through 4 for the four levels of biodegradation listed in table. Bioaccumulation might be given a score of 1 through 3 based on the three categories of bioconcentration factor. Similar scores could be developed for toxicity. So these indexes or scores could then be combined, for example, by adding the scores to arrive at a composite index. Okay, so these are some of the ways how we can find out uh, the gravity of the property. Okay, the degree of seriousness or the importance of the property. Okay, so let us take an example, classifying fuel molecules. So let us compare the soil absorption, water solubility, and biodegradation of three compounds, okay, that have been used in gasoline. One is ethanol, one is methyl tert butyl ether or MTBE, and one is isohexane. So let us take these three compounds and use this data to assess which of the chemicals, if spilled on land, would be more likely to migrate to surface or groundwater. Isohexane is one of the most commonly found molecules in gasoline derived from petroleum. Ethanol is commonly obtained from corn grain, and MTBE was produced in large quantities in the United States from methanol derived from natural gas and light petroleum gases, which is isobutylene. Okay, so these are some of the compounds. One is ethanol, one is methyl tert butyl ether, and one is isohexane. Okay, so if you refer to the literature by Allen and Schonard as per 2001, so these are the values. Okay, properties for these compounds can be determined through property databases, okay, or using methods described in this literature. So ethanol has a CAS registry number of 641755. So these are some representative number for this compound. MTB is 1634044, isohexane is 107835, So the soil absorption log KOC value will be 0.3, 1.3, and 2.0. Water solubility ppm, okay, so it is in parts per million. So it is infinite for ethanol, 40,000 for MTBE, and 14 for isohexane. And the biodegradation half-life, it is days to weeks for only 3. The results indicate that petroleum-derived gasoline, if spilled onto ground, is more likely to absorb to soils than MTBE and ethanol, making it less likely to migrate to water sources and cause water contamination. In contrast, however, MTBE and ethanol have been added to gasoline because of provisions of the Clean Air Act that are designed to reduce emissions of air pollutants. So these are some of the observations based on the study, okay, based on the values obtained. So now let us go to the next lecture, which is on green sustainable materials. Okay, so almost every engineering design involves the use of materials. If an engineering design is to be as sustainable as possible, the materials that are involved in the embodiment of the design should have light, environmental, and natural resource use footprints. Determining the magnitude of a material's footprint is not straightforward. However, in this lecture, a three-pronged approach to characterizing the footprint of materials will be described. Okay. So firstly, a material must first be extracted and purified, refined, and the overall impact of this extraction and refining is the first component of the footprint. Once the material enters the production system, it can be reused and recycled, reducing the need for extraction processes. The extent to which various materials are reused and recycled, and the energy and other sources used in processing the materials, is a second component of the footprint. Finally, if a material is not reused or recycled but escapes into the environment, its environmental fate, persistence, human health impact, and ecological impact are a third component of the footprint. So these are some of the that these are some of the approaches, basically three approaches to characterize the footprint of materials. Okay, as has been described here. So, environmental and natural response use footprints of materials extraction and refining. So, this is one of the simplest approaches for characterizing the footprints associated with the extraction and production of a material to assess the material's overall scarcity. If we simply state it, if a material is scarce, it is likely to be energy intensive to obtain and refine it, and the ability to meet large scale demand will be limited. Elements will vary widely in their natural abundance. The most common elements on a mass basis are, in descending order, oxygen, silicon, aluminum, iron, calcium, magnesium, and potassium. All of these elements are present at greater than 1% abundance in the Earth's crust, and all are present in widely used commodity materials. However, in contrast, some widely used elements such as silver, tin, antimony are present at the ppm level or lower on average in the crust. Okay. So this is a table which shows the abundance of selected elements in the Earth's crust in terms of mass abundance. Okay, so you can see the elements here and the abundance here in terms of percentages and parts per million units. Okay, so this is the sources. The literature is Taylor 1964. Also, this is a figure which shows the annual production of elements for use in commerce. So these are the examples of elements shown, and this is the production per year in million grams. Okay, that is 10 to the power 6. This into 10 to the power 6. Okay? So if you see here, annual production of the maximum production of element is iron Fe. Okay. So now let us take an example problem. So supplies and use of elements. So let us like problem is we need to calculate the ratio of the abundance of materials in the Earth's crust, which is in tons, to the annual use of the materials, which is in tons per year. Assume an approximate mass for the crust of 2 into 10 to the power 9 metric tons. This mass is based on a 40-kilometer thickness for continental crust and a 3-kilometer thickness for oceanic crust with an average density of 3 gram per centimeter cube, which is 3 tons per meter cube. So this is the table basically. So these are the elements. So this is the abundance in crust. Okay. So 5.6% is basically 0.056 into 2 into 10 to the power 19, because this is the approximate mass for the crust. Okay. So this much tons or metric tons. So the use is provided in tons per year. Okay, so we need to find the ratio of abundance to use year. Okay, in terms of year. Okay, so 70 ppm means 70 by 10 to the power 6. Million is 10 to the power 6, right? So 70 by 10 to the power 6 into 2 into 10 to the power 19, this value. Okay, so if you calculate the ratio of abundance, so how to calculate? We just need to divide this value. Okay, this value, like for example 5.6 is 0.056 into 2 into 10 to the power 19. So this value we need to divide by this value. Okay, so we will get the year. Okay, ratio of abundance to use here. So if you see here, we have divided by 1.2 into 10 to the power 9. Here we divided by 12.5 into 10 to the power 6. So we'll get these values: 1 into 10 to the power 9, 10 to the power 8, 10 to the power 9. So similarly 877. Okay, so so this presents the scenario of all the material present in the crust can be extracted. Not all material can be extracted. Concentration too low to be extracted cost effectively. There is a relationship between the total crustal abundance identified and economically extractable deposits, that is reserves. On average, only 1 in 10 to the power 7 to 10 to the power 9 tons of an element in the crust is an economically viable reserve of the material. Okay, so there is the relationship between total crustal abundance and reserves. Okay, so this is the reserves in tons and this is abundance in crust tons. Okay, so abundance is much more as compared to the reserves. Okay, and all the elements fall in basically this between these two lines. Okay, so there is gold, platinum, cadmium, silver, lead, vanadium, copper, phosphate, potash, titanium, magnesium, aluminum, iron, oil, coal, everything. Okay, so similarly, let us see this problem also similar. So calculate the ratio of the economically extractable materials in the Earth's crust reserves to the annual use of the materials in tons per year. The quantities of reserves identified in this exercise are derived from the US Geological Survey USGS 2010. Okay, so these are the elements: economically extractable resources. These are the values in tons, and use, these are the tons per year. So we need to find the ratio of abundance to use in year. Okay, so the solution, say for iron Fe case, the ratio of abundance to use here is basically nothing but, as I told you in the last problem. So it is basically dividing this value by this value. Okay, so here 230 into 10 to the power 9 divided by 1.2 into 10 to the power 9, so it will give 191 years or 190 years. Okay, so similarly, if you divide 400,000 by 22,000, you will get 17. Okay, so these are the values. So now let us see about extractable supplies and use of materials. Although the total amount of material available in the Earth's crust is sufficient to support current rates of extraction indefinitely, from as we saw in the example one, the second example, however, shows that the total amount of crustal material that is present in high enough concentrations to be economically recoverable is much lower than the total amount available. Okay, so if you saw in this, okay, this their ratio of abundance was very high. Okay, so 10 to the power 9 years is like infinite. Okay, but if you actually see how much is actually usable, okay, so it is very less. Okay, 190, 100, 152, 200. See this, 17 silver will finish in 17 years. SB is antimony, right? So it will finish in 10 years. Tin will finish in 19 years. So it is very serious. Okay, so the second example shows that the total amount of crustal material that is present in high enough concentrations to be economically recoverable is much lower than the total amount available. This is because energy and other processes required to mine and purify the material for use is much higher. Okay, so there comes the concept of Sherwood relationship. Okay, Sherwood relationship. So this relationship was basically coined by a person called Sherwood, named Sherwood. So this is an approximate relationship between the concentration at which a material is found in a raw material and the cost to refine that material. Okay, so this concept, that is the cost of a material, is largely determined by the cost of extracting and purifying the raw material. Okay, so is sometimes referred to as the Sherwood relationship. Okay, so the relationship between prices and dilution in ores, the Sherwood relationship, is technologically dependent. As technologies continue to become more efficient, costs associated with material extraction can be reduced. A certain amount of entropy, that is energy, must be overcome to purify a material, and that imposes a minimum energy burden that must be overcome. So this is basically the Sherwood relationship. So it is plot between price, which is US dollars per pound, in terms of dilution, that is inverse of concentration, that is 1 by kg metal by kg ore. Okay, so or kg ore by kg metal. Okay, so figure 3 mix metal prices in 2004 as a function of dilution, which is 1 by concentration of metals and commercial ores. The relationship illustrates the concept that the more dilute a material is in its native ore, the more expensive it will be to purify into a commodity material. So from this, let us see the energy burdens of material recovery. So to recover resources from raw materials, the minimum amount of energy that must be invested to concentrate the material is determined by the entropy that must be overcome in the purification. To make an estimate of this energy, calculate the entropy of mixing that must be overcome in concentrating 1 kg of a metal present at 0.2 parts per million mole fraction basis in water. Imagine a process that seeks to harvest lithium from seawater to manufacture lithium ion batteries. The entropy of mixing is given by delta S equal to minus R summation xi ln xi. So where delta S is the molar entropy of mixing, R is the gas constant, xi is the mole fraction of each component in the mixture, and the summation is done over all components in the mixture. So lithium has an atomic weight of 6.94. So B, the minimum energy required for separation, that is the energy required to overcome changes in entropy, it is given by delta G equal to T delta S. So these are some of the standard definitions. Okay, so these definitions of entropy. Okay, so you will find this in thermodynamics and chemistry. So the minimum energy required for separation, that is the energy required to overcome changes in entropy, is given by delta G equal to T delta S, where delta G is the Gibbs free energy of mixing and T is the absolute temperature. So this is a reserve classification for minerals as per the McElvey diagram. Okay, so one is identified resources and one is undiscovered resources. And how can they be segregated as economic, marginally economic, and sub-economic? So let us see. So reserves that are known and their extent demonstrated can be recovered at cost lower than current prices. Okay, and they are referred as economically recoverable reserves, and demonstrated reserves that could be cost effectively recovered through either moderate improvements in technology or increases in price. They are referred to as marginal reserves. Demonstrated reserves that are unlikely to be recoverable at any foreseeable price are referred to as sub-economic, and demonstrated reserves can also lead to inferences that similar geologic informations may contain similar reserves. These are referred to as inferred reserves, which can be economic, marginal, or sub-economic. So if you see here the supplies of the elements, okay, so there based on the extent of supply you can classify the various elements. So these have the infinite supplies. Okay, these elements, these have the ample supplies, these have the adequate supply, these have potentially limited supply, and these have potentially highly limited supply. Okay, so this has been taken from Gradle and Allen by Source, 1995. So the multiple elements are present together in minerals. Example, copper ores typically contain As, that is maybe arsenic, Sc is maybe cerium, and T is thallium. Pt, platinum ores typically contain Ir, iridium, Os I don't know, I have to check. Pa maybe palladium, Rh I forgot, and Ru is ruthenium. Okay, so rhodium maybe Rh. So please check these elements in the element table. So the elements with the highest demand or highest price tends to drive the extraction of these ores. For example, mining of lead and zinc produce cadmium as a byproduct, making it available at a price and a quantity that might not be possible if it were not associated with zinc. Okay, so therefore, tracking material flow in engineered systems. So materials have a life cycle. So they are extracted from the lithosphere to biosphere, processed into commodity materials, then products, then used and possibly reused, then eventually disposed of or leaked into the environment. The number of times that a material is reused or recycled before it is released into the environment can have a significant impact on its environmental footprint. In addition, different types of uses for the same material can lead to very different types of impacts. So, characterizing the flows and emissions of materials in manufacturing and use requires data on material and mineral flows entering the economy and information on the waste emissions and recycling structures. So this is basically a conceptual framework of analyzing material flows as per the National Research Council 2003. So this is a system boundary. Within this is the accumulation in system. So inputs are basically domestic extraction, direct and indirect, and imports direct, indirect, and outputs result in basically waste emissions, outputs, and exports. Okay. So, example of that material flow and analysis, let us take the example of lead, okay, PB. So, it is a neurotoxin, and lead exposure is associated with developmental delays, okay. So, it may result in lead poisoning, okay. Historically, some of the principal uses of lead have been as an octane enhancer in gasoline, in batteries, and in paint. The material flows of lead in the United States in 1970, and in the mid 1990s are shown in next slide. So we'll see here, okay, and uh, this one, as shown in the left hand portion of the diagram, flows of lead comes from both extraction of geological resources, virgin materials, and recycled material. So I think this slide has been missed here. So basically it tries to explain the material flow analysis, okay. So in 1970, 70, the fraction of recycled material was 36%. That was 450 tons recycled per 1,250 tons total usage. While in the mid 1990s, the fraction had increased to 65%. That is 910 tons recycled by 1400 tons total usage. The lead is incorporated into a variety of products. Okay, some products when used as design, such as lead paint applied outdoors or lead additives is in gasoline, result in the release of lead into the environment, dissipative uses, and other products when used as design, lead acid batteries, can be effectively recovered and recycled at the end of the product's life, which is non-dissipative uses. Figure shows that the fraction of dissipative uses decreased significantly from 1970 until the mid 1990s, in part because of the phase out of many lead-based paints and lead additives in gasoline. Use of lead in batteries increased significantly from 1970 through the mid 1990s as the demand for starting, lighting, ignition batteries in vehicles had increased. So this is basically figure 4.7. It shows the global flows of iron in 2000. Okay. So the bigger is the arrow size, higher is the flux. Flux is basically the amount of the amount of energy per unit area. Basically the flow per unit area. Okay. The amount of lines, flow lines per unit intensity basically. So it is the energy flow per unit area. So it is the flux. Okay. So bigger is the arrow size, greater is the amount of iron flowing. Okay. So here it is in 800 trillion, okay, trillion grams iron per annum. So that is 10 to the power 9 kg. Okay. So trillion is 10 to the power 12 in terms of gram. If you convert to kg, it is 10 to the power 9. Okay. So this is the amount of iron flowing, okay, per unit annum. So per annually. Okay. So per particular area. Okay. So it is amount of iron flowing. So similarly, the additional flow types can be incorporated. Okay. So global use of iron as a case study, it separates iron flows during production of products into production, fabrication, manufacturing, use, and waste management. There are flows between these stages of materials processing. For example, is home scrap within production operations is reprocessed. Flows of crude ore from the lithosphere, that is the virgin ore, can be compared to various types of recycling. Losses to the environment can be compared to total use and stocks. So the global material balance for iron. So material flow information of the type shown in figure 4.7. So that is this one. Okay. So typically comes from multiple sources, and material balances can be used to assess the consistency of the information. At the most microscopic level, the basic material balance equation in out accumulation can be translated into crude ore in flows to repositories stock accumulation. So this is also a flow of iron in the United States in 2000, and this is the flow of iron in China 2000. Okay, so these are the values are a little different, but processes are same. Intensity flux is different. Okay. In figure 4.9, it shows the importing and exporting of iron by countries ranked by net imports minus exports. Okay. So if you see here, the export in trillion grams iron per annum. So the maximum is Brazil, then Australia, Russia, Canada, Romania, and in terms of import, okay, so maximum is by US, okay, followed by Japan, China, Germany, France, UK, Netherlands, Poland, Hong Kong, Austria, Czech Republic, and Belgium, okay. So they have shown the iron ore, iron and steel products, parts and final products, scrap, and total net import export, okay. So from there, the global import export of iron, so based on the chart, okay, this chart, we can find that understanding the source or sourcing of materials and the geopolitical issues associated with source regions will become increasingly important as global demands on resources increase. The world's leading exporter of iron is Brazil, and the leading importer, both total imports and net imports, imports exports, is the United imports minus exports. Okay, so it is the United States. Okay, so leading importer is US, leading exporter is Brazil, as you can see from this. Okay. Countries such as Belgium, the Netherlands, and the United Kingdom are both importers of iron as a raw material and exporters of iron in manufactured goods. Okay? Global trading community materials lead to some countries becoming net importers while others are net exporters depending on the material. For example, while China is a net importer of iron, it is a dominant producer and exporter of rare earth metals. Combinations of materials scarcity, potential energy savings, and geopolitical factors may lead to increased rates of recycling and reuse for many materials. So this table basically shows the percentage of metals in hazardous waste in the United States that can be recovered economically. Okay, so these are the metals. The percent theoretically recoverable is this much. Okay, so it lies between 74% or 68% up to 100% based on different metals. And the percent recycled in 1986 is this much. Okay, so it is very less as compared to the theoretical percentage. Okay, because of the inherent costs associated with your this one recovery. Okay, so recovery and recycle, the inherent cost associated is very high, and also based on the dilution. Okay, so that is one of the some of the issues associated for the less recycling as compared to the theoretical potential. So these values have been taken as per Allen and Behemanish literature from 1994. So as per that literature, this very focused analysis, which is shown in table 4.3, this one. So yeah, so it was initially performed in 1994, and it led to the conclusion that many opportunities existed for recovering materials from waste. The limitations to analysis was that the analysis focused only on hazardous waste, where legal liability concerns may limit the desire to recycle. Okay, and the identification of recyclable streams was simplistic. It ignored issues related to economies of scale, that is, processing geographically dispersed, heterogeneous waste streams may be more expensive than extracting a relatively homogeneous ore. And nevertheless, the analysis indicated that resources are not effectively recovered from many waste streams. So, as per the UNEP, that is United Nations Environment Program, okay, UNEP study, the United Nations has assembled more recent global data on metals recycling. You can go through this website, and its analysis continues to conclude that global recycling rates can continue to be improved. Metals like lead, along with iron, chromium, cobalt, nickel, copper, zinc, and many precious metals, have post-consumer recycling rates that exceed 50% globally. But many other metals, example rare earth metals, have post-consumer recycling rates of less than 1%. United Nations, and as per the UNEP 2011, one of the primary barriers to using waste as raw materials is a lack of critical information on waste streams. While a large number of data sources are available on waste streams, they lack critical information that is needed to assess whether the waste streams might be reused. Data on the composition of waste, their location, and co-contaminants are rarely available, yet are critical to evaluating the potential use of waste as raw materials. So the material flow summary, material flow tracking can identify overall availability of materials and potential opportunities for material reuse or recycling. One way to review these flows is as an opportunity to change the designs of industrial systems so that they more closely resemble highly networked mass conserving natural ecosystems and industrial ecology. The data necessary to perform detailed material tracking are just beginning to emerge in a consistent framework. For many analysis, we need to assemble the necessary data on material use and flows on a case-specific basis. As material scarcity becomes an important issue, these types of analysis will become increasingly very valuable. Okay? So from all these discussions we have done so far, so the basic summary is almost every engineering design involves the use of materials, and these materials have environmental footprints. This week's lecture basically summarized the methods for characterizing the footprints associated with extraction, processing, and environmental releases of materials. But these assessments can lead to very different characterizations of materials. So the question is the material scarce? Can it be recycled? Do environmental releases have significant impacts? There are no universally accepted methods for combining these characterizations of whether a material is sustainable. Multiple methods are used. Engineers will need to consider materials in the context of particular designs, recognizing that the choice of the most sustainable materials will be application specific. Okay. So with this, we have come to the end of the lecture part. Okay, so now let us try to understand it even better, even more in more depth by solving some problems based on that. Let us go through the problems. So the first question is, which of the uh, which of the following fate? Okay, so fate is basically release of a contaminant into the environment. So which of the following fate and transport phenomena occurs for gasoline after gasoline spill? Okay, so is it vaporization to atmosphere A, B vapor diffusion in soil, C dissolved plume to groundwater, or D all of the above? So out of A, B, C, D, which is the correct option? So if you remember this slide and this photo, so the gasoline spill fate and transport schematics. So based on this, there will be residue in the upper side of the soil, and that will result in vapor diffusion. So this one, vapor diffusion in soil is correct. So secondly, there is vapor released to atmosphere. So therefore, vaporization to atmosphere is also correct. And thirdly, there is plume generated, dissolved plume. So dissolved plume to groundwater is also correct. So all the three correct options are correct. That is D. Okay, all of the above. So D, all of the above is the correct option. So as you can see, D, all of the above is the correct option. Second question: the process by which the contaminant is carried by the media as the media flows through is called A. Diffusion, B. Dispersion, C. Advection, D. Turbulence. So out of A, B, C, D, which is the correct option? So basically, advection is the phenomenon where the media carry the contaminant as the media flows through. Okay? So this basically the moving of the contaminant, okay, by the media, okay, the carrying of the contaminant by the media through its flow is basically nothing but advection. Okay, it is a particular term here, so that's why it is called advection. Okay, so dispersion diffusion, that is basically related to like flowing in a concentration. Okay, so basically from higher concentration to low concentration, but that is not the case with advection. Okay, so any contaminant, if it is flowed by the media, it is basically advection. So C is the correct option. So C, advection, is the correct option. Third question: what is the significance of bioconcentration factor BCF? A. It characterizes the magnification of concentration through bioturbation. B. It characterizes the magnification of concentration through food chain. C. It characterizes the equilibrium concentration for organics waste in water. D. It characterizes the equilibrium concentration for organics waste in air. Okay, so out of A, B, C, D, which is the correct option? So if you remember these terminologies, so bioconcentration factor is basically it is a ratio of chemicals concentration in the tissue of an aquatic organism to its or concentration in water. So CaO by Cw. Okay, and it characterizes the magnification of concentrations through the food chain. Okay, so it characterizes the magnification of concentration through food chain. Okay, so that is the B. B is the correct option. So as you can see, B characterizes the magnification of concentration through food chain is the correct option. Fourth question: calculate the expected concentration of trichloroethylene TCE in the fish taken from the waters containing a concentration of TCE equal to 4 milligram per liter. The bioconcentration factor BCF for TCE is 11.2 liter per kg. So which is the correct option? Which is the correct concentration of TCE? Okay, so is it 0.448 milligram per kg? Is it 31.8 milligram per kg? Is it 0.318 milligram per kg, or is it 44.8 milligram per kg? Okay, so basically if you saw the if you remember the last slide, so this we need to find out the CaO value. Okay, So this is nothing but equal to BCF into CW, where CW is the concentration in water. Okay. So BCF value is 11.2 liter per kg. Concentration in water is fish taken from the waters containing a concentration of 4 milligram per liter. So it is BCF into CW. Okay. So 11.2 into 4, that is 44.8. Okay. 44.8 milligram per kg. So this D 44.8 milligram per kg is the correct option. So same has been shown here. TC concentration is in fishes, TC concentration in water into BCF, that is 4 milligram per liter into 11.2 liter per kg, that is 44.8 milligram per kg of fish. So D 44.8 milligram per kg is the correct option. Fifth question, what is Sherwood relationship? A. It is a relationship between the environmental impact of raw material extraction and the environmental impact of refining the material. B. It is a relationship between the concentration at which a material is found in the raw material and the environmental impact of refining the material. C. It is a relationship between the environmental impact of raw material extraction and the cost to refine the material. D. It is a relationship between the concentration at which a material is found in a raw material and the cost to refine the material. So out of A, B, C, and D, which is the correct option? So if you remember, it is basically an approximate relationship. Okay, Sherwood relationships are an approximate relationships between the concentration at which a material is found in a raw material and the cost to refine the structure. So that is basically it is a concentration at which a material is found. Okay, and in a raw material is found in a raw material. Okay, so A and C are not correct option. So it will be between B and D, and the cost to refine the material. Okay, not the environmental impact of refining the material. It is cost to refine the material. So D, relationship between concentration at which a material is found in a raw material and the cost to refine the material. So stereo relationship is concentration at which a material is found in a raw material and the cost to refine the material. So D is the correct option. So as you can see, D is the correct option. Sixth question, choose the incorrect option. A, the first component of footprint is associated with the impact of extraction or mining and refining of the material. B, the second component of the footprint is associated with the policies around interstate and inter-country transport of this material. C, the second component of footprint is associated with the impact of recycling and reusing the material. D, the third component of the footprint is associated with the impact of final disposal and environmental fate of the material. So A, B, C, and D out of them, which is the incorrect option? So let us see a three. If you remember, a three-pronged approach to characterizing the footprint of materials. So first was a material must first be extracted and purified or refined, and the overall impact of this extraction and refining is the first component of the footprint. So it is extraction and mining and refining of the material is correct. Okay, so A is not incorrect. Once the material enters the production system, it can be reused and recycled, reducing the need for extraction processes. The extent to which various materials are used and recycled and the energy and other resources used in processing the materials is a second component of the footprint. Okay, so reuse and recycling. Okay, so this one, recycling and reuse. So C is the correct option. Okay, so with the policies around interstate and inter-country transport of, so there is nothing like the second component for characterizing footprint of material. It is nothing related to policies around interstate and inter-country transport. So B is the incorrect option. And let us see D. So finally, if a material is not reused or recycled but escapes into the environment, its environmental fate, persistence, human health impact, and ecological impact are a third component of the footprint. So the third component is associated with the impact of final disposal and environmental fate of the material. Okay, so D is also correct. So which is incorrect? Only B. Okay, so B is the correct option. So as you can see, B, the second component of the footprint is associated with the policies around interstate and inter-country transport of this material is the correct option. Seventh question, what are the considerations for a good LCA? A, screening approach to filter the more potent processes and data by a preliminary LCA exercise. B, compared systems need not have same functional unit. C, impact assessment is done by peer-reviewed methods like Impact 2002 plus, Recipe, etc. Or D, sensitivity analysis and uncertainty evaluation is not necessary. So out of A, B, C, and D, which is the correct option? Okay. So hint. So considerations means there can be more than one option. Okay, what are the correct options? So considerations for a good LCA includes screening approach to filter the more potent processes and data by a preliminary LCA exercise. So screening approach is correct. Okay, so he is correct. Okay, complete systems must have a same functional unit, but here it is written need not have same functional unit. So this is not this can be considered for a good LCA. Okay, so B is incorrect. C, impact assessment is done by peer-reviewed methods like Impact 2002 plus, Recipe, etc. So this impact assessment is done by peer-reviewed methods, okay, like Impact 2000 plus and 2002 plus and Recipe. So C is correct. And sensitivity analysis and uncertainty evaluation is done to test the robustness of results. Okay, so this is important. It is not unnecessary. Okay, it is not necessary is wrong. Okay, so B and D are not correct. A and C are the considerations required for a these are the some of the considerations required for a good LCA. So A and C are the correct options. So as you can see, A, screening approach to filter the more potent processes and data by preliminary LC exercise. And C, impact assessment is done by peer-reviewed methods like Impact 2002 plus, Recipe, etc. are the correct options. Eighth question: which of the following factors can lead to an increased rate of recycling and reuse of materials? A, geopolitical factors, B, material scarcity, C, transmittance of materials, or D, energy savings. So out of A, B, C and D, which is the correct option? So hint: combinations of material scarcity, potential energy savings, and geopolitical factors may lead to increased rates of recycling and reuse for many materials. So that means what are the factors that can lead to increased rate of recycling and reuse of materials? So one is geopolitical factor, correct. Okay, so A is correct. Material scarcity, so that is also correct. Okay, so B is correct. Transmittance of materials, so that is not correct. Okay, so C is incorrect. And D, energy savings, so energy saving is also there. So D is also correct. Okay, so which of the following factors can lead to an increased rate of recycling and reuse of materials? So leaving C all. Okay, A, B and D. There's A, geopolitical factors, B, material scarcity, and D, energy savings. Okay, A, B and D are the correct options. So as you can see, A, accepted answers are A, geopolitical factors, B, material scarcity, and D, energy savings. Okay, so these are the correct options. Ninth question: while a large number of data sources are available on waste streams, they lack critical information that is needed to assess whether the waste streams might be reused and recycled. Which of the following are critical information with regards to above statement? A, composition of waste, B, details about co-contaminants, C, location of waste, or D, volume of waste stream. So out of A, B, C and D, uh, which of them are the correct critical information with regards to the above statement? Okay. So if you remember this slide, some of the last slides in the discussion, like lecture discussion. So this UNEP has assembled more recent global data on metals recycling. Okay, so from that, if you see the composition of waste, okay, so which of the following are critical information with regards to the above statement? So composition of waste. So basically, while a large number of data sources are available on waste streams, they lack critical information that is needed to assess whether the waste streams might be reused and recycled. Okay, so that is true because see, because of this, if you can see in this slide, data on the composition of waste, their location and co-contaminants are rarely available, yet are critical to evaluating the potential use of waste as raw materials. So they are very critical to evaluating the potential use of waste as raw materials, but their data, that is data on composition of waste, location and co-contaminants are rarely available. So this is true. Okay, this is true, this is true, and this is true. A, B and C are true. And volume of waste stream is like it is not scarce. Okay, so it is, they don't lack critical information on volume of waste stream. Okay, because while a large number of data sources are available on waste streams, so that means large number of data is available on volume of waste streams. Okay, so what are the critical information with regards to the above statement? So because they lack critical information uh, on composition of waste, details about co-contaminants and location of waste. Okay, to assess whether the waste streams might be reused and recycled. So which of the following are critical information? A, B and C. D is not critical because they have a large number of data sources are available on waste streams. Okay. So what are the this one? If you see what are the correct options, so it is A, B, and C. Okay. So these are the critical information basically. The volume of waste stream is not critical because they have large number of data source. Okay. So A, B, and C are the correct options. So if you see A, composition of waste, B, details about co-contaminants, and C, location of waste is the are the correct options. Okay. 10th question, which of the following statements are true? A, material flow tracking can identify potential opportunities for use. B, for scarce materials, material flow tracking is highly valuable. C, material flow tracking helps in developing material testing equipment. Or D, for abundant materials, material flow tracking is of least importance. So out of A, B, C, and D, which of the which are the correct? Which of the following statements are true? Okay. So if you remember the material flow summary, let us again study. So material flow tracking can identify overall availability of materials and potential opportunities for material reuse or recycling. One way to view this flow season is as an opportunity to change the designs of industrial systems so that they more closely resemble highly networked, mass conserving natural ecosystems and industrial ecology. The data necessary to perform detailed material tracking are just beginning to emerge in a consistent framework. For many analysis, we need to assemble the necessary data on material use and flows on a case specific basis. As material scarcity becomes an important issue, these types of analysis will become increasingly valuable. Okay, so material flow tracking can identify potential opportunities for reuse. Okay, so that is true. So it can identify overall availability of materials and potential opportunities for material reuse or recycling. So A is true. For scarce materials, material flow tracking is highly valuable. So that is also yeah. So this is also true. As material scarcity becomes an important issue, these types of analysis will become increasingly valuable. So that is true. See, material flow tracking helps in developing material testing equipment. So that is wrong. Okay. So it helps to identify overall availability of materials and potential opportunities for material reuse or recycling, not on developing material testing equipment. Okay. So this is not true. And D, for abundant materials, material flow tracking is of least importance. So that is also not true. Okay, so it is not of for abundant materials. It is not of least importance because it provides an opportunity to change the designs of industrial systems so that they more closely resemble highly networked, mass conserving natural ecosystems and industrial ecology. Okay, so they may help in more efficiency and more optimization on making a highly networked mass conserving natural ecosystem. Okay, so that is why it is basically it is important even for abundant materials. Okay, it is not only important for scarce materials but also important for abundant materials. Okay, because of because it provides a opportunity to change the designs of industrial systems so that they more closely resemble highly networked mass conserving systems. Okay, so C and D are the incorrect options. The correct options are A and B. Material flow tracking can identify potential opportunities for use. That is correct. And for scarce materials, material flow tracking is highly valuable. That is also correct. Okay, so A and B are the correct options. So as you can see, A, material flow tracking can identify potential opportunities for use, and B, for scarce materials, material flow tracking is highly valuable. So these are the correct options. Okay. So with this, we come to the end of today's discussion. Okay. So let us meet next week and start our discussion on the 7-week lecture and problem solving. So with this, I would like to end today's discussion. Bye. Good night.